Now, I may have told you that one of my favorite viewing nights ever was spending the night on a beach in Costa Rica, a very, very secluded beach. You couldn't even drive there. You had to actually hike through the jungle to get to this beach, and spent the night on that beach. And throughout the night, watching the sky turn. I was watching the Milky Way and how it shifted as, of course, the Earth is turning. But it looks like the sky is turning around us. And that's what all ancient people thought. They thought the sky was like a giant globe spinning around us, like living in a fishbowl that's rotating and spinning around us. That idea is called the celestial sphere. My little term for that, in iBooks, this will be an important thing to put in your glossary. It's like an imaginary space globe around the Earth. An imaginary space globe around the Earth. Art team, this might be something you could work on as a project, making some kind of celestial sphere. That would be a really cool project to try to make. And I'll show you some stuff that would go on in here in a second. Now, this idea has been around since ancient times. And as ancient people learned more, they kept trying to change their model to incorporate what they knew. For example, they began to realize that the sun and the earth, the sun and the moon, are closer to the earth than the planets and then the stars. Okay? Or some of the planets. So anyway, what they started doing was coming up with a layer of spheres. Like the inner layer might be just for the sun and the moon. And then you'd have another sphere for the planets. One of my favorite ideas that they had in ancient times, somebody said that beyond the final sphere was heaven. But that final sphere has pinholes in it so that the light of heaven can shine through. What do we call those pinholes? The stars. I think that's kind of a cool idea. I think that's kind of beautiful. But anyway, that's how the ancient people were explaining the sky. But believe it or not, we actually still kind of use this idea. Because what it does, it allows us to have sort of a globe in the sky. So that allows us to give locations in the sky. Just like we have the states, or like the constellations, but that's not all that specific. I mean, if I say something is located in California, that gives you an idea, but where in California? It's a huge state, and there are a lot of different regions, right? So we need a way in the sky to pinpoint locations, and that's what we're going to talk about today. So, the first thing we do in the sky is, if you stood at the North Pole and shined a laser straight up into space, that laser is what we call the North Celestial Pole. There's a North Pole in the sky. There's a South Pole. We take the equator and we extend it out into space, and we call it the celestial equator. So just imagine this globe in the sky. Now, having said that, if I want to pinpoint a location on Earth, let's say I wanted to tell you the location of some little island in the Pacific Ocean. How do I do that? How do I pinpoint its location? Tell you exactly where it is. Go ahead. Latitude and longitude. Guess what we have in the sky? The equivalent of latitude and longitude in the sky. Now, this gets a little annoying for a couple different reasons. And not much I can do about it until I'm the head of NASA, and then I'll change it. Okay? But until then, here's a minor annoyance. Instead of calling it latitude, they call it declination in the sky. But it works exactly the same way. It's in degrees. So on the Earth, what latitude is the equator? 0. What latitude are we at in South Florida? 26 degrees. What latitude is the North Pole?
0.
Now you got it. North Pole is 90. Equator 0. You go up to 90. Okay, how about this? How about the South Pole?
360.
That's right. Negative 90. That's how latitude works. Now, in the sky, guys, if you're reading an article in research, in the research group, and you're reading an article and they're talking about a star like Fomalhaut, and they mention a negative declination, you know immediately that's a southern hemisphere star. And the closer it is to negative 90, the farther south it is, right? At some point you're reading and you think, well, that's not a star we're going to see at astronomy night, right? If it's at negative 80 degrees declination, I would have to be, in Argentina to see that one. You got it? That's how it works. Mildly annoying because they call it something different, but that's not too bad. It's still latitude. Okay, research group. What is longitude in space called? Very good. Right ascension. They learned this in the video yesterday, is why I'm asking them. Right ascension and declination. Now, right ascension, I said, is the equivalent of longitude. Right ascension is the equivalent of longitude. Again, the name itself is annoying because it's kind of a long name. It's a mouthful. But here's the most annoying part. We use angles just like we do for latitude, except they don't use degrees. The angles that they use are called, you ready? Hours, minutes, and seconds. But it's not time. That's not confusing at all, right? Nah. So we're going to use some new angles. Now what I like to do, add this to your notes. I want you to write the word ARC above both of these. Arc minutes and arc seconds. I'll refer to them that way so hopefully you don't confuse them with time, minutes, and seconds. But they're an angle. Here's how it works. You can think of the sky. Think about horizontal lines in the sky, just like latitude. And then we're going to have these sort of wedges in the sky that are the longitude, the right ascension. And what they've done is they've taken the whole sky and divided it up into 24 hours. Now, if you take 360 degrees and divide it into 24 hours, that's 15 degrees per hour. So every wedge in the sky, every wedge that we call an hour is about a 15-degree wedge of sky. Does that make sense? Every hour is 15 degrees. Guess how many arc minutes are in every hour? 60. That's the only good news, is that the math is exactly the same as the math is for time. So on a test, you don't have to freak out about it, guys. If I asked you on the test how many minutes are in 2 hours, I think you could figure that out, right? You wouldn't freak out about it. So on the test, if I say how many arc minutes, you know what I mean, are in 2 hours, then, it's 120. You've got that. The math is the same, okay? Any questions on that? We'll practice that. If that's going to be on the test, we practice it. But anyway, that's how it works. Now, you may be wondering to yourself, why? Why would they do this to us? Why not just use degrees? Why have this confusing thing? Well, I'm a bit of a history buff. And so when I can research and find out the history of something, I'll usually share it with you. And I think this is very interesting anyway. Here was the problem they had. Hundreds of years ago, when they would sail, let's say across the Atlantic, how did they find their latitude? The North Star, right? And they could measure the angle. Research group, what instrument did they use? Nice, a sextant. Okay, and they'd measure that angle. And that was their latitude. But here's the problem. If you're sailing west from Spain in the 1600s, you know your latitude, but you have no way of knowing your longitude. So let's say you're sailing across the Atlantic and you discover a new island. And you need to tell people where this island is. Well, you don't know how far you went. You have no way of knowing. But all you can say is, hey, it's at 31 degrees latitude, and I sailed west for 10 hours. You had to give it as a time. Why is that a terrible system of giving distance? What do you not know? The speed. You don't know how fast you were going. One day in 10 hours, the wind's blowing in your direction, You know what I mean? And you go really far in 10 hours. And another day you don't hardly go anywhere in 10 hours, but guess what? That's all they had to do. I mean, that's all they had at their disposal. They didn't have a good way to do longitude. By the 1700s, the problem was so annoying, this is a true story, that they called it just the longitude problem. The British government offered anybody $1 million, the equivalent of $1 million, to solve the longitude problem. And I want to say the guy's name was Harrison, like John something Harrison. But anyway, there was a guy that worked on this for decades, and he finally won the money. And what he did, he didn't use a different system. He actually designed a clock, a mechanical clock that could work on a ship. All the previous clocks, with the ship rocking back and forth, the clocks wouldn't work right on a ship. So he at least got a clock that would work, well on a ship. Kind of an interesting story there, little tidbit of history. But that's how time got involved. Hours, minutes, and seconds, because that's all they could use for a long time for longitude. When I say celestial sphere, this is the picture I want you to envision. That's the celestial sphere. iBooks, I'll throw this, we're going to set up a Dropbox account, and I want this picture in your iBook for sure. Or you can just, probably Google it and find it real quick and throw it in. Okay? The celestial sphere picture like this, show your readers what that looks like. Okay? And again, art crew, something you could think about building, something along those lines. Now, just to take a look here, this is what ancient people thought was happening. Why they were seeing different constellations through the night rotating and stuff like that. That's how they envisioned Earth sitting there static and the globe turning around us, that kind of thing. So, just a refresher here on latitude and longitude, except in the sky, the equator becomes the celestial equator. It's at 0. You go up to 90. You go down to -90. Now, longitude. The equator is an obvious place to start from. But there's no obvious place to start longitude from. Or, again, in space, what we call right ascension. So we start here. The celestial meridian is just an extension of what? What do we call that on the Earth? The prime meridian. Question, where does the prime meridian start on the Earth? That's right, Greenwich, England. A little town outside of London. Now, why in the world, what's that? No. Just outside of London, just down the Thames River. Question, why in the world would, of all the places on planet Earth, why this little town, why did they start 0? Well, I decided to do a little research on this myself. So, and every once in a while, this kind of thing will be in the notes. I'm going to be sharing vacation pictures with you. So, I like to do little explorations while I'm traveling. So guess what? The last time I was in London, I thought, I'm going to go over to Greenwich and find out what the deal is. So, and if you want to hear a little, maybe funny tidbit about this. So, I'm on vacation with my wife at the time. And I know that she is not interested in either astronomy or history. And there's no way in the world she's going to spend an afternoon going to look at some, because here's what I knew. I knew that Greenwich had what was called the Royal Observatory. Okay? So basically, in the late 1800s, why did they start at Greenwich? Because number one, England ruled the world, right? And so they got to say, hey, everybody, you start with us. Yeah, everything's measured from us. And where in England? Well, the Royal Observatory. So they started the 0 line at the Royal Observatory. So I thought, hey, while we're here, I want to go check out this Royal Observatory. Knowing my wife is not interested in this at all, I'm thinking, how can I do this? How can I do this? So we're walking down the streets of London one day, and I'm like, honey, guess what I heard? I heard that this little town of Greenwich has the best shopping in all of London. Her eyes get big. I'm like, yeah, let's go. You want to go check it out? Sure, that's awesome. So anyway, so we take a boat down the Thames River, And this is the village of Greenwich here. And we go walking through the village, and every time we go by some stores, she keeps going, are those the stores you're talking about? I'm like, no, 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 I hear it's further in. And then we finally get to this giant field, and then you can see the observatory up on the hill. And then she just stops, and she's like, we're not going shopping, are we? I'm like, no. But anyway, we got up there. It was really, really neat. They actually were giving the tour of the observatory, and I convinced them to open the observatory for me. They actually opened it up to the sky and stuff like that to show me. I wanted to see the mechanics of how it worked and everything. It was really nice of them. But anyway, outside in the grounds of the observatory, they had some old instruments and stuff like that. But I saw a bunch of tourists lined up, and I walk over to see what they're doing. Check this out. It's kind of funny. There's a metal line going right through the grounds of the observatory. Guess what that line is? That's the prime meridian. That's exactly where it starts. And so all the tourists, goofy tourists like myself, take a picture where you're standing there and you can say that half of your body's in the eastern hemisphere and half of your body's in the western hemisphere. All right. Anyway, and luckily she thought it was pretty cool, so she wasn't too mad. All right. Now, when you set out and you watch the sky, what looks like the sky turning, something interesting happens. And this is a challenge that I want for our photography team. Photography team, pay attention. If you go out and you set up a camera in a dark place, you set up a camera in a dark place, and you let it go for 10, 15 minutes, here's what starts to happen. If you just take one long exposure, here's what happens. You see the sky turning. Of course, that's really what's happening. The earth turning. But the stars make what we call star trails in the picture. Really beautiful pictures. And so this is what the photography teams in the different classes are being challenged to do. This picture is interesting because some other stuff got involved here. We have an airplane trail that got in there during the picture. And even cooler. A what? A meteor. Very good. Shooting star. Yeah, isn't that cool? Now, you can't plan that. You just have to get lucky. So that's always fun to try to catch something like that. All right, let me show you the best one that I've taken, personally. This was in the Everglades a couple years ago, and I kept the camera on for half an hour. Now keep in mind, where I was at, it was super dark, or at least it seemed that way. It was really, really dark, and I left the camera on for half an hour, and I was kind of shocked at what it looked like when I got it exposed there. Now, this was kind of a special astronomy night. There were some college kids back in town, my former students, so we went out together one night in the Glades there. And what is this? The North Star. So I purposely set up the camera to point exactly at the North Star. And you notice the North Star is the one star that doesn't rotate. Okay? And anyway, I was really happy with the picture. It took the camera half an hour to process the picture. So what we did was we took the picture, we looked at other things, we took the picture, the camera starts exposing. Well, I had given a couple guys a ride out there, so they're riding home with me. Well, right when we got back to Coral Springs, it finally came up on the screen, and we were just shocked at how light it was. We couldn't see anything. The only thing I did expect, there was one light in the distance that I thought was probably coming from one of the sugar plants out there. And that was it. That's the only light we could see anywhere. I was amazed at how light the picture was along the horizon. And the thing that shocked me the most, we had no idea that these poles were there. It just freaked us out. It was so cool that just suddenly popped up on the screen. Like, whoa, there was a road there, It was awesome. Anyway, I'm going to show you, I need to add this to the slides. I'm going to show you some pictures that the guys took last year in astrophotography group that were better than mine. Mike Berendi and Brian Weissman and those guys, their pictures were better than mine. They took some awesome ones. I'm going to add those to the notes for Monday. In the meantime, here's some I found on the internet. Yeah, amazing stuff. Now you notice this one's not pointed towards the north anymore, right? Not towards the North Star. As a matter of fact, it looks like they're kind of curving this way and kind of curving that way. And right here in the middle, it looks like pretty flat. Where was this picture taken? The equator. Very good. That's at the equator. I love this next one. Check this out. Question. Where is this pointed? Ah, nice. Some of you caught that. This is towards the South Pole because there's no bright star in the middle. That's how you know immediately where a star trail was taken, right? If you can see a star there or not. You can also see little patches here of both the Milky Way and what are called the large and small Magellanic Clouds. That was taken at the tip of Argentina, actually. North or south? North. This next one, in the Himalayas. Check this out. Beautiful, beautiful picture. Isn't that gorgeous? And then finally, this next one is a good example. Listen, guys, with your own pictures, right? Before you go post them on Instagram or whatever, a lot of you probably, change them a little bit, right? Throw them in Photoshop and change certain things, right? Well, astronomers do the same things, and they color their pictures and they change little things. But to me, at some point, it goes a little too far. Let me give you an example of one that, in my opinion, maybe goes a step too far in sort of the processing. You can judge for yourself. It's beautiful. Right? Gorgeous picture, but it might cross that line. You know what I mean? Like, is that a legit picture? Is that real? Well, it's a real picture. I have no doubt that this guy set up a camera and did this. But of course, it looks like he's been coloring it quite a bit. You know what I mean? For sure. And maybe some other little processing tricks. So that's, when you see stuff on the internet, keep in mind that astronomers can change their pictures. They're usually colored a little bit. But sometimes, in my opinion, maybe they go a little too far. You guys have any questions on today's lecture? Okay, well, thanks for listening.